to the R video tutorial on generating distributions. I'm going to call it by brute force. What we're going to use is only the uniform distribution. We're not going to do really any hard arithmetic or calculus or anything like that. This is just to show properties of random variables and how they go together. This will be the first part in a series of these where you learn how to generate random numbers from a variety of sources. All right, so what I've done is I said, how many samples do I want to pull, right? Because I'm random sampling. How many do I want? Here I'm going to pull 1,000 of them. And the reason I've organized my window this way is I've got the plots up over here because I'm going to make lots of pictures. I'm not really interested in the output at the moment. All right, so if I have 1,000 of these, notice it shows up here, shows up here. I want to generate some uniforms, and if you remember from a previous video, to get a uniform, we're going to use RUNFIF. The first number is how many of them I want, and this is the lower bound and the upper bound. All right, so if I run this, I'm going to get U1, which is 1,000 numbers, and I can look at a histogram of this real quick just to see what it looks like. And you notice here that almost all the values are equally likely. And if I were to rerun this, I'll get different pictures. And they should be pretty flat. No real value along this axis is any more likely, because that's what these bars correspond to. How likely is a point? These are all about equally likely. Now what we want to do is see what we can do to create more of these. So what I'm going to do is I'm going to try to see what happens when I add these together. So just hang on here with me. So add two uniforms together. And if you've taken a mathematical statistics course, you've done this from a theory perspective, but maybe not from seeing it actually work. So I'm going to have here U1, and I'm going to do copy and paste because we love copy and paste. And I'm going to do the same thing and have U2. And I'm going to just add them together. So I'm going to make this A1 because I'm adding them together. U1 plus U2. And then we'll just look at what the histogram of this looks like. All right. So if I run all of this together. Now notice these are independent uniforms. One doesn't depend on the other. But notice how this picture changes. It now goes from 0 to 2, which would make sense because we're going from 0 to 1. I'm taking things and adding them together. But notice that the points near 0 and near 2 are much less likely than the ones near 1, which kind of makes sense as well. But this isn't actually a triangular distribution. And we're being able to create other types of distributions just from using samples from a uniform. Now, we can extend this out to a ridiculous amount. So what I'm going to do is I'm going to do this. I'm going to create some space here, and I'm going to create a bunch of these. Okay? So you just have to bear with me. So I'm going to add 12 uniforms together. And you'll see why at the end. Add 12 uniforms, distribution, or they're not distributions. I'll just put together, because they're random variates from it. So I'm going to have to do a lot of copy and paste. If you're following along, I'm going to be adding them together as well. 12 is a magic number in this case for some other reasons. So what I'm going to do is copy and paste this a bunch of times so that I can set this up. And what I'm going to be able to do is sample from something that looks quite similar to a distribution you've seen if you've taken any other statistics class. One of the most popular distributions. I'm not going to be able to sample from it exactly, but I will be able to get really, really close to what's considered a normal distribution to be able to sample from it just by adding uniforms together. And we'll actually explore that here in just a second. So now I have to type in U3 plus U4. And I really should have did a loop here. If you're a good programmer, you would have done a loop. You're probably saying, Ed, why in the world are you making me type all of this? But I'm trying to keep this simple for those who are not as well versed in programming yet. So here I'm going to keep going. So I'm going to keep going with this plus U10 plus U11 plus U12. And I'm going to name this thing A2 because it's the second thing we added together. And I'm just going to get a histogram of it. and we'll see what this looks like. Provided I did everything right, and bingo, it works. It looks pretty good. And we get a histogram here. Did we get all 12 of them? Do we get an error somewhere along the way? Oh, yeah, I forgot to put the plus sign over here. So this is important. Whenever you're playing with things, make sure you test things. So make sure they work right. Now let's see if this works. Okay, this looks better. Still not as beautiful as I would like it to be, but it's much better in the sense that it's centered at 6. I've added 12 things together that are between 0 and 1. Each of them has a half as its mean. If I add those together, and I were just to simply subtract off 6 here, I will get something that's even closer to a standard normal. Okay, so notice now it's centered at 0. It goes between -3 and 3, pretty much. Isn't that what most of your normal distributions look like? And we can actually create one here in a second. But what I want to do is I want to look at a plot here, QQ norm of this thing. QQ norm gives us a QQ plot, and it will tell us whether or not this is at least approximately normally distributed, and it would look like a 45-degree angle if it were. And boy, does that look kind of like a 45-degree angle, and it's quite good here in the middle. Now out at the end, you see it starts wobbling away, but here this looks like a 45-degree angle, and it wobbles away out here at the ends as well. But that's probably due to randomness. Now what we can do is we can also do, there's a Shapiro-Wilks test on this, which is a test for normality. And so we can run this, and then I'll bring it up over here real quick. And based off of this, the Shapiro-Wilks test is, the null hypothesis is the data is normally distributed. Okay? So this p-value is not below any reasonable threshold. So if you were to use a test to see whether or not this data was normally distributed, you would conclude that it is based off of this test. So what do? We chained a whole bunch of uniforms together, and we came up with a normal distribution. Some other things we could do to this real quick before we hop off here, I know this is going to run long, is just take the mean of this and make sure that it looks like a standard normal. The mean should be near 0, and the standard deviation should be around 1, if this is truly a standard normal distribution. And sure enough, look at that. Really close to 0, really close to 1. All right, so we've brute forced a normal distribution together just using the sum of uniforms. And this is one way to generate random data. Now, this is not the only way. There's lots of other ways, but I want to show you that you can use properties of random variables that you may have learned in a mathematical statistics class, and they actually work. All right, so we're going to stop here, so I'll see you in the next video.